What does quantum mechanics tell us about the world? This is a question that we've already asked on this podcast, and you might say, I have the answer. David Wallace told us it's the Everett interpretation. We live in a branching multiverse. But today we're going to present a very different view on things. Our guest is Ruediger Schack. Ruediger is a professor of mathematics at the Royal Holloway University of London. He spends his time working at the coalface of quantum mechanics on problems in quantum information and quantum cryptography, but he's also, along with Carlton and Chris Fuchs, one of the originators of a very different way of interpreting quantum mechanics, QBism. You might recall from the discussion with David Wallace that key to understanding what quantum mechanics tells us is the measurement problem, the apparent collapse of the wavefunction when measurements are taken. Now, in common with David, Ruediger believes there is no measurement problem, but he believes that for very different reasons. David thinks that everything happens. Ruediger thinks that actually when a measurement is taken, there is a collapse in the wavefunction, but that's not a problem because the wavefunction doesn't represent an underlying state of reality. It just represents the state of your knowledge. It's an epistemic object. So when you take a measurement, of course your knowledge updates. That's discontinuous, but it's not mysterious. What I really enjoy about this conversation is that it's a very fresh take on understanding quantum mechanics. And it also draws in insights from phenomenology and continental philosophy, from people like Merleau-Ponty. Now, for someone trained in the analytic tradition, such as myself, this is unfamiliar territory, and it's really fun to explore. And that's what I hope to get from this podcast. Ways of exploring different worlds and different conceptions of the world. I'm James Robinson. This is Multiverses. Ruediger Schack, thank you so much for joining me on Multiverses.
It's a pleasure.
So I think around 20 years ago, you embarked on a program with some others to create a new interpretation of quantum mechanics, a new way of understanding what it's telling us. So that would have been about 80 years after quantum mechanics first emerged as a theory, and 80 years over which it's been incredibly predictively successful. So my first question is, what is it about quantum mechanics that, despite all that predictive success, motivated you to think, well, we still need to do some thinking to understand what it is that quantum mechanics tells us? What's difficult about quantum mechanics in that sense?
Well, that's a big question. First of all, you always mentioned the enormous predictive success, and I mean, we all agree that quantum mechanics is the most successful theory that physics ever has come up with or has created. On the other hand, these now 100 years have seen discussions on the meaning of quantum mechanics which have never stopped and in some ways never made much progress. So while on the one hand quantum mechanics is has enormous predictive power, on the other hand, there's still the same discussions about what it means about how to interpret quantum mechanics that, well, we had 50 years ago, 80 years ago, etc. So that is one background. There's something more specific. Myself, and that's only, well, it's partially true also for Chris Fuchs. It's true for Carl and myself, because the QBism this arose from this very fruitful early discussions between Carlton, Christopher Fuchs, and myself in Albuquerque. We were thinking about the meaning of probability and interpretation of probability, and were very dissatisfied with frequentists or let's say objective interpretations of probability, because they get you stuck in statistical mechanics. So the interpretation of probability was for me the first the first step towards thinking about the interpretation of quantum mechanics. Now, we all know that quantum mechanics probability is a quantum mechanics is a probabilistic theory. Probability plays a central role in quantum mechanics. And I think I believe what Ed James said, that I'm probably just paraphrasing him, there's no hope understanding quantum mechanics before you actually understand probability. And so my thinking of probability was what got me started first. I'm thinking about quantum mechanics in this way.
Okay, interesting. And I guess to kind of give a little summary for listeners who might not have caught, there's a previous episode with David Wallace where we go into some more detail on the kind of fundamental difficulties at the heart of quantum mechanics. But as you allude to, they're around probability, and maybe more specifically, you kind of have two laws. If you open kind of an elementary textbook on quantum mechanics, you might find something saying, okay, you've got two kind of equations of motion, if you like. One is a very familiar sort of wave equation, which is saying everything's evolving quite smoothly. You have some states that are obeying this wave equation. Very nice. And then there's another rule, which is kind of where the probability comes in, which says, oh, when you do something, when you try and measure something, you need to take your states from your first equation and apply something called the Born rule, which kind of collapses them down. And I guess it's that, it's that almost dichotomy or the fact that we have two rules, one which looks to physicists quite familiar in that it's a wave equation, and one that looks quite unfamiliar in that it seems to demand that the observer is playing an important role. And when they are taking a measurement, suddenly there's a new rule that's applied. And it seems that this is where QBism has something quite interesting to say. So, in short, what does the QBism say about what is your kind of the program view on what's going on here?
Well, in this, if you look at this dichotomy or these two elements of the quantum formalism, then QBism, I think, is at exactly the opposite point of the spectrum for many worlds, where in many worlds the main focus is on the wave equation, on the what's called the unitary evolution, or the law of evolution of the state vector. And in QBism, we de-emphasize this very strongly. This is actually not an important part. It's certainly not the starting point. And of course, it's important in many ways, but it's not foundationally important. The deterministic time evolution of the wave vector. Instead, the starting point for QBism is measurement. And just just that part, which in standard formulations would be associated with something like collapse of the wave function, etc., which is not the term which we actually use. So it's measurement that's the starting point. Of course, you then immediately would ask, well, what is measurement? And you also mentioned the observer. Now, QBists, you will notice, never speak of the observer. We actually
That's right.
we prefer to talk about agents instead. That is that is important, because observer. So we're still talking about measurement, right? In a measurement, if you talk about an observer, that suggests that the observer just observes something that already exists. And measurement very often, if you think of measuring the length of an object in everyday language, you of course think, well, the object has a length and I'm just measuring it and determine it. And an observer also reinforces this picture of measurement as finding something that already exists. In QBism, a measurement is always an action. It's an action that an agent, let's say, if it's a quantum measurement, is a physicist taking an action on some system. The the agent participates in the bringing about a measurement outcome. So it's not discovering a pre-existing measurement outcome, but the act of measurement participates in the creation of the outcome. And what the quantum formalism gives us, now just in a nutshell what QBism says about the quantum formalism, quantum mechanics, the rules of quantum mechanics serve as a guide to action. They guide the agent in their actions.
Brilliant. And so I want to pick up firstly on something you mentioned right at the beginning there, which is that the emphasis for kind of many worlds in interpretation is on the wave function, and that's unmysterious, whereas this perceived collapse, and I agree, I don't think there is a collapse, is the thing that needs careful thought. Whereas on the qubist perspective, well, this perceived collapse is entirely to be understood as a function of just our Bayesian updating, I think, right? So once you are, when you are preparing your experiment, you're anticipating that you're going to find something. You don't know what it is. And of course, it makes sense that when you find it, there's a kind of discontinuous movement in your beliefs. And I think that's the key thing, obviously, for QBists, that the movement, the change that's happening is not a change in the world. It's not a change in a objective fact about the world. There's no collapse of some object, a wave function. Rather, there's an updating of our beliefs, if I understand it correctly. And I think that's what's interesting to me is in some ways both the many worlds interpretation and the QBists want to say there is no measurement problem, right? They say that for very, very different reasons, but I think there's an agreement that there's not an issue there with measurement. The many worldsers go a sort of hyper-realist route where they say, well, the wave function is so real that all the different things that it's telling us do occur. Whereas the QBists say almost the opposite. The wave function is not an element of reality at all. And reality is somehow co-created, I guess, between the agent and the quantum system. But it's not a pre-existing thing that we can read off about the world. Is that a fair kind of reinterpretation or summary?
Yeah, it's not bad. I think that's pretty accurate. So you clearly did your homework. Thank you for that.
Thank you.
I would say that was a pretty good characterization also of the difference between the two approaches. What QBism isn't doing. Okay, what you mentioned the predictive power or the success of quantum mechanics as a predictive tool. QBists would say as a guide to action, which is for us is an important difference. But in any case, it gives us. It allows us to manipulate the world to also to make predictions, to build devices, to do experiments, all kinds, in a way that was never done before. The step that what you call realist, hyper realist or whatever, what most interpretations of quantum mechanics do, they actually take the mathematical objects, formulas, the measurement object of quantum mechanics, of the theory, and I would say then they mistake them for the reality. If you see what people are actually doing when they're using quantum mechanics, you would say they're using this formalism for prediction. I would say they're using it as a guide for action. But anybody who uses it, and people who use it are the ones who actually who turned it into this very, very, very successful thing. The success is measured by what you can do with it. Nowhere is it necessary or even, I think, suggested that these mathematical constructions you have, they are that they correspond to something in the real world. So that is an additional step you're taking. You're saying you have a very successful theory. It has all kinds of abstract objects it manipulates. So these must be somehow correspond to real things out there.
Mm-hmm.
Sometimes this is called reification of things to use. Now, this is something that many worlds is doing and something that QBism isn't doing.
Yeah, I think that's a really important distinction to get out there. And I mean, I first want to say that I think it seems to be a common misconception of QBism that it is not realist at all. But I think it's just not realist about quantum states in particular. So, and as you say, the kind of laws that we have under the QBist perspective, I've seen them often described as normative. So rather than being laws of nature that are describing some underlying reality, they are laws that we should seek to follow if we want to sort of get on well with the world, as it were. So they're guides to action in that they're normative. I guess where I struggle here, because I feel that all makes sense, but where I struggle is the realist picture in general gives a good reason for why we should follow those laws. So they say, well, they're not normative. they're actually reading off some facts about nature. And I'd say, we could sort of make this normative movement for any theory of physics. We could take, Newtonian physics of billiard balls and say, well, actually, Newtonian mechanics is not telling us something about the real world. It's just telling us how we should set our beliefs about what's going to happen in games of snooker and in planetary motions, but it's not actually telling us that there are forces out there and so forth. And then I think my move there and my move with quantum mechanics is to say, well, look, if these are giving us such a good guide to action, what is the reason for that? And maybe the reason is that there's something about that guide that is capturing elements of reality. I mean, this is just, I've restated in very long format, inference to the best explanation or abduction, right? And that, if you have a theory that's working really well in some predictive sense, maybe the best explanation of that is that it's actually capturing something real about the world. How, big question, how does QBism think about that?
That's an interesting question. Here's one take on it. So how do we know why do we describe the world in terms of forces and particles, etc.? Ultimately, because that works extremely well. So we have done experiments, and we have physics is an experimental science. So all the theories, the terms we use to do physics, like forces, particles, mass, etc., we all use them because they work extremely well. So, and now you're trying to explain why they work well. Well, it seems to be circular to me, right? Because you postulate, or you actually come up with these theoretical constructs because they work well, and then you say, now I understand why they work well, because this is how the work is. So I think that is somewhat circular and doesn't give you much. QBism, on the other hand, is more direct. We have, so to actually say something more clearly that you also mentioned, the QBism believes that the rules of quantum mechanics tell us something about reality. So the world has a property which makes these particular rules a good normative principle, a good guide for action. So often, QBists say that this is some this is the kind of realism that QBism aims for. It's saying something about the world, and the rules of quantum mechanics understood normatively, understood as answering the question, how should I act? They actually are, if you want, a a, a real feature of the real world. So, and asking, well, so in that sense, I believe the answer QBism gives to why does it work is more direct, because the world has a feature which says that if you follow these rules, you will be successful, and it's objective. So I don't know whether I want to necessarily call this a form of realism. It's certainly an objective rule in the sense that everybody can use it. So unlike a quantum state, which I mean, should be going to get to this point, a quantum state or probability in QBism is always one agent's personal subjective belief. The rules of quantum mechanics are objective in that any agent can use them. In that sense, they say something about the world. I'm slightly cautious here only for the following reasons. So QBism understands itself as a realist project in the sense that it wants to actually learn something about the world. It wants to find out what the world is like. That is, I believe, much harder to do than if you are a standard realist where the world just consists of certain objects. You have a third person view of them. Coming up with a say an ontology that takes the agent where the subject and the object both are central is hard. And there are some there are philosophical or areas of philosophy that try to answer the same question. There's pragmatism, but in particular there's phenomenology, and recently we have been in a very fruitful dialogue with phenomenologists. Now, phenomenologists would actually not would not describe the quantum formalism as a feature of reality, because they are even more radical. They want to just start the entire project from building it up from the phenomena, so that something like the quantum formalism would come later and would not be described in their view as a real as a pre-existing part of reality. So this is why I qualify this slightly. But I certainly would say that the quantum formalism is objective, and and it gives us because it's normative. It gives us a very direct answer of why it works, because that is an objective rule which says something about the world, which tells us directly what to do, and so therefore, yeah, you might say long-winded.
Okay, yeah,
That makes answer to that question.
No, I think I think I'm understanding the position, and maybe to contrast it with the kind of more standardly realist picture, which would be something like you have these rules, and then we need to look sort of further than them for the objects that they seem to suggest exist, and those are the objects that we're going to place our faith in as kind of members of reality. And it seems, and I might be mischaracterizing here, but that the QBist is saying something like, no, we have the rules. The rules are real. The rules are objective. We can all obey them. But don't try to look further than that. And maybe that's why you say it's a much more direct explanation. Does that ring true, or? And I know, by the way, yeah.
No, here's the first time I actually really disagree with you. I would not say don't look further. The whole project of formula. I mean,
Okay.
Cubism has maybe Cubism has three big projects. One is interpret quantum mechanics, and we've done that. We've actually we understand and we can say exactly what every term in quantum mechanics means and how it's used. So it's an interpretation of quantum mechanics. The second bit is derive quantum mechanics from simple principles. And that would give
Right.
us actually more also insight for why it works, etc. So that's an ongoing project, and there has been a lot of progress has been made there, and is being made, but it's certainly not complete. And then there is the biggest project. Go beyond go beyond just the quantum formalism. Tell us what it tells us about the world. So
Right.
we
Okay.
definitely do not want to stop there. We want to understand what the world is like, and actually we have very clear ideas of what that should look like. The in that respect, philosophically, so sort of going beyond the quantum mechanics, the biggest difference between quantum mechanics between Cubism and most other interpretations of quantum mechanics is that, well, in Cubism describes it's often called a participatory view of the world. Um, Agents participate in creating the universe, which implies, and this is an important part of it, the universe is unfinished. It's not just there. It does not afford an outside view. There's no God's eye view of the world. There's no third person view of the world because it's an unfinished thing. And in that sense, it's I think a much more it's a much better view of the world. It's a much more interesting view of the world. I regard something like many worlds as rather sterile. You've got, I mean, think of it. You have what's your ontology? What is ultimately the world? It's a state vector which sits in an abstract Hilbert space, and it evolves according to a deterministic equation. So essentially it's all there. Once you have a snapshot of the thing at one time, you can actually follow it backwards and forwards, and the entire universe is just sitting there in front of you. There's a static view of the universe, whereas Cubism points to a well to a view of the world that is an unfinished world, a world where every system has autonomy. So by see, we have a here's another shot at the fallacy that comes from identifying the objects of your theory with the whole thing, with everything,
Mhm.
with the world. So, because I just before I only mentioned one aspect of this, which is that you have these mathematical constructs and they're very successful. And so you think, oh, that must correspond to things in the world. You can actually go one step further and say, oh, it's so successful, therefore they must be all there is that's in the world. And many
Right.
worlds, I think, is quite culpable of that. They say it's so successful, therefore all the world is this big wave function. Whereas Cubism says, well, there is actually no evidence for that at all. We and Cubism says whenever we use quantum mechanics to model or to make predictions or to act on a quantum system, we only ever capture certain very well prescribed aspects of that. It's never the whole thing. We're not
Mhm.
saying that the wave function you write down for a system just in some sense captures everything about the system. And we will say that every system we approach in this way, we apply quantum mechanics to, has autonomy. So this is why the state we ascribe to the system, is not we ascribe to the system. It's not a description of the system. It just captures our expectations of what we would experience what we will experience when we act on the system. It leaves the system its autonomy. So the world is I think, a far more interesting and far more open and dynamic place than any third-person view can capture, according to QBists. So all this was an answer to your suggestion that QBism wants to stop there at the, let's say,
Okay.
at the level of making predictions. And no, we don't want to stop. We want to go far beyond that.
Good. Okay, so I'm glad that it's more ambitious than and I think I had that flavor, so maybe I was being a little bit provocative there. And I mean, you mentioned a lot of interesting things there I want to pick on. I first just want to say, I guess on the sterility of the many worlds, I mean, certainly it's completely deterministic under the many worlds, or the universe under the many worlds interpretation is completely deterministic. And I guess just very briefly, their response would be something like, well, all the interesting things like agency, are real, features of the world in as much as they're very, powerful patterns of explaining things, and that kind of gives them legitimacy in your theories. But they're emergent, and I think that's maybe an interesting, again, point of difference here, where perhaps what the QBist is saying is, well, actually, it's fundamental to our way of understanding things that if you look at quantum mechanics, the agent is really, does feel like an important element of that. And it's not one of these weird mathematical elements that just we can't figure out how to sit within reality, but it's naturally telling us that agents are playing an important role, again, in the kind of co-creation or in this participatory realist picture of things. And therefore, we need to give agents a kind of not just emergent status, but like a kind of fundamental ontic status, to use a term of art. Is agenthood, I guess, one of the things in the QBist picture that is playing an explanatory role, or is an agent just another emergent feature of the world, or is it not such a simple dichotomy?
I think it's neither. In the sense, it is simple. So quantum mechanics is, and let's say physics in general, from a QBist perspective, is, as we mentioned before, a guide to action. And so it is well, it's a guide to action for agents. So that means that within quantum mechanics, agents, well, here's something. So it's in a sense, it's an addition to decision theory, quantum mechanics. It's not describing the world. So it's not a theory that describes how agents emerge. For instance, if you wanted to ask this question, you can ask questions like that, but they always have a different flavor. They always, so quantum mechanics would always give you well, if you can apply it to other agents. Well, obviously, because quantum mechanics can be applied to any system, but you always need to remember that when I apply quantum mechanics to some other agent or so, that all I'm doing is I'm just using the formalism to quantify and organize my expectations upon, well, acting on that system, that other agent. So that's what the role of quantum mechanics is, and therefore it's quite limited in that way. Asking to define agent within quantum mechanics is in that view akin to asking, well, if somebody uses probability theory or classical decision theory, well, before that goes off the ground, first you need to define agents within probability theory, user of the theory. So they're just different categories. The user of the theory
So
is. Yeah,
So
I have
if
to
I'm getting
finish
this
it.
right, sorry.
No, I didn't. I actually didn't even know how to finish the sentence, so that's
Maybe I'm doing you a favor. I have the same myself often. I wish that sometimes I would be interrupted as my thoughts trail off.
exactly.
I guess then, yeah, I think that, as you say, you can apply. So under the QBist perspective, you can actually apply, quantum mechanics to agents, but I guess you can never completely remove all agents from the picture, because there's always someone doing the quantum mechanics, as it were, and that's, I guess, key to this. Maybe that's one of the things, as you were pointing to, with phenomenology that is falling out, where you're saying, okay, here the structure necessarily is, or at least under this, which we think is our best interpretation of quantum mechanics, the structure of the world is such that, there is no objective in the term of God's eye view of reality. There's always, our most fundamental theory, our best theory, at least, of the world is one which, I don't know if it demands agents, but a lot of the sort of interesting experimental results, actually, if you want to apply that theory, which we do, it demands agents, and it demands at least one agent who's preparing experiments. And I'm not sure. This is probably where you need to interrupt me, because I'm not sure how to take that.
I'm happy to interrupt you. There is, again, quite a number of things which I might say here. In phenomenology, one of the important, the starting point is that there's no way to understand a subject without the world, or without the object. No way to understand the object without the subject. They're always you could call them different aspects of the same underlying fundamental thing. But I think no matter how you then describe this any further, they cannot be separated. So there's no third person, no third person view of the world, but there's also no independent. So the agent is also never just in itself without the world.
Right.
There are two poles, or two aspects of the same underlying thing. So when you at least twice, or probably twice, mentioned this idea whether or not there should be at least one agent, and that is the idea of just there being one agent is very far from QBism. QBism, the world is populated of lots of agents. That sounds very much like a third-person view, but it isn't. There's some very nice way in which Merleau-Ponty brings in other agents as almost a necessity of defining yourself. He has this view, has this thought experiment, or the observation that you cannot see the back of your own head. So in order to, but you clearly you have a view of yourself as a person. How can you have that? And so he says that in order to constitute yourself as an agent, as a subject, you actually need the perspective of other subjects. It's another way of saying that the subject cannot be thought independently of the world. It goes further and says a subject can actually not think itself independently of other subjects. And in that way, you have multiple, going back to the language of QBism, multiple agents almost as a necessity. In QBism, there's another way of expressing this. There's this big, we always stress that other systems, any other parts of the world, have autonomy. So when we write down a quantum state for another system, well, repeating that phrase, this only captures my expectations for the consequences of my future actions. It does not constrain the other system in any way. It's not that quantum states together with the laws of quantum mechanics don't tell the other system what to do. The other system has fundamental autonomy.
Yeah. That makes sense. So, there is no, it's not meaningful, at least in the world that we live in, where we acknowledge there's lots of agents. There's no kind of, it's very anti-idealist or anti-solipsist, I guess, in that there's no sort of one person who's calling the shots here, right? It's co-created by everyone. And I have a couple of nice quotes from Merleau-Ponty, and thanks for sort of pointing me to him, which I thought I'd just throw in here as some kind of, I feel like they echo what you were saying. So one thing that he said was there is no world without a human being, or without human beings in the world. And I feel that captures this idea that the phenomenologists and also the QBists are neither objective realists in the sense of there being the possibility of a world without some kind of agent, I guess, or rather the world is co-created with kind of external features plus agents together. But it also captures the fact that there is some kind of external reality. It's not just idealism. There is, I guess, in Merleau-Ponty's terms, there is this kind of flash which is linking things, and maybe in Cubist terms, that's the actions of agents. The other quote, I'm just going to see if I can find it here, that I have from him. Written down many things. Oh yes, so it's, I think, and this is maybe more controversial, and maybe where phenomenology and Cubism diverge. But Merleau-Ponty at some point said that, I think it's in the Phenomenology of Perception, he wrote that phenomenology is a matter of describing, not of explaining or analyzing. And he kind of clarified, I think, his meaning a bit there by saying it's a method of returning to the thing themselves, to things in themselves, I guess, rather than imposing kind of further structure around those things to explain them. I mean, I think you've already stated that Cubism does seek to be explanatory, but perhaps there's an element of what Merleau-Ponty is saying here, that it's trying to, phenomenology is trying to describe things in themselves. Does that feel in the spirit of Cubism, if not the idea of laying aside the ambition of explanation?
Yeah. Well, I'm not an expert in phenomenology, and so it's a bit. I'm not that. Feel a little. Some hesitation to comment more about this, but here's one thing. In any phenomenological reconstruction
It's a tricky word.
of the world, so quantum mechanics, Cubism, comes very late. It's so. Cubism only starts. Quantum mechanics only starts to appear when there is an agent, and actually, quantum mechanics has to be a physicist. It has to be a very well educated agent who has identified a system. So there's already a very clear split between the subject and the object. The physicist will have to have identified a physical system that. To make an experiment on, to query in some way, writes down a quantum state. So this all comes very late in a phenomenological constitution of the world or so. So in that sense, one must be careful not to try to compare these enterprises too closely. Phenomenology So QBism, here's one bit where phenomenology for QBism is in some sense more ambitious, or maybe has a different starting point. Phenomenology is pure philosophy. You just observe your experiences. There is this thing called epoche where you just try to get rid of all your preconceptions and start from with just your basic your unanalyzed experiences. So Cubism, we believe that our view of the world, our conception of reality of the world is really motivated, is almost compelled by quantum mechanics itself. So it's sort of empirical in that way. It comes from the particular features of the quantum formalism. And phenomenologists would not say this normally. So we think that there are reasons. If you look at the formula, if you look at quantum mechanics, you can see why we make certain choices, and you're compelled to a certain view of the world. And so that's the QBist project. So it is physics more than just it is physics driving philosophy more than the other way around, even though there should be really conversions of ideas, etc. So it's not just one direction, but physics plays a major role in that whole enterprise.
Yeah, that makes sense. So yeah, the motivations are different, but they sort of somewhat converge. Not completely overlapping, I think, are on a similar view of the world, which is one that goes, I guess, against the grain of kind of thousands of years of the kind of traditional way of understanding things, of an objective reality. And I feel like one needs very strong motivations to give up that picture. I want to come back to some of the, maybe let's sharpen up this intuition a little bit. So one of the things I wanted to touch on was the EPR criterion of reality. So in the sort of the famous Einstein Rosen-Podolsky paper where they talk about entanglement, they put down a criterion which is something like this: if you can predict with absolute certainty the outcome of or the value of some certain variable, I'm paraphrasing here, then there's some element of reality which kind of corresponds to that variable. And I guess kind of rephrasing that in kind of more simple terms, if you know, I think this comes back actually to this original point around the simplest way of explaining why laws work seems to often be that there's some straightforward way in which those laws are capturing elements of reality. And I think that's the intuition behind the EPI criterion, right? If you can for sure say that something's going to be, that some pointer is going to point at a certain value, then, whatever theory is, whatever that value is, it's kind of representing something real about reality. And then, of course, the way that this gets carried through is, well, you can set things up so that you can know with certainty, the values of a quantum state. And if that's the case, well, isn't the quantum state itself something real? And I know there's so how does a QBist kind of think about that?
Well, QBism certainly rejects the EPR criterion of reality. Yes. One reason is that the EPR criterion of reality leads to big trouble in quantum mechanics, as we know. It leads to this idea of non-locality, which is this science fiction sounding idea that you can You can change something here and instantaneously, let's say on Sirius or some faraway star, something real changes. It's that's a direct consequence of the EPR criterion of reality plus quantum mechanics.
Yes.
So this kind of non-locality, which is, for instance, goes against anything that Einstein believed about the world. There is a much simpler way of actually seeing what's wrong with this. It's a category mistake. If I believe something with certainty, why does it mean there's something? I mean, I could just be wrong. It's just my belief, and my belief has no hold on the world. So for a qubist, there is no fundamental difference between writing down a probability 1/2 for something and probability 1.
Right.
It just expresses my belief. Probabilities do that, and that seems a very, very obvious point that I must not never even the community of physicists can be wrong about something even if they believe it with certainty. Probability 1 does not mean there's an element of reality connected to it. That's just a category mistake.
I think that's a strong response. I think that really captures it. One still feels, or one might still feel that, there is a justification to have a categorical difference between, almost certain of something and just knowing something, right? Based on facts. But I'll accept. I mean, I think this is like a rabbit hole we can
expand this very slightly. So it's a very common way of embedding probability in logic, where true and false correspond to probability 1 and 0, and so regarding probability theory as an extension of logic. Now, in that context, it makes perfect sense to identify probability 1 with truth and probability 0 with falsehood. But in QBism is based on a interpretation of probability, well, in terms of action, decision theory, where probabilities, their role is to inform action.
Mm-hmm.
And so all a probability 1 then says is, it really says, well, you will bet everything you own on an outcome because you write on probability 1 for it. So that's all it means.
Mm-hmm.
It just is a numerical expression of the kind of action you're willing to take.
Yeah, good. And before I think I want to discuss some other pieces here, but I think this is like an important. I just want to restate the fact that I guess this locality problem is one of the kind of key things that QBists would say we're successful on that, right? If you want locality, like the many worlds interpretation, that's one of the things we offer. So again, in common with many worlds, you're both saying, okay, there's no measurement problem, and there's no issue with locality. And again, the reasons for making those claims are completely opposite on the kind of every atom or many worlds view. Locality is preserved, and maybe very briefly, the EPR experiment is, have these two entangled particles, and it seems naively that if one is on one side of the universe and the other is on the other, and you perform an operation on one, it's going to instantaneously affect the state of the other. The many worlds folks will say, no, there is actually, things have already by this point kind of split into two branches of the wave function, or they're splitting as you run the experiment, and you discover that in one world, both particles were already in a kind of aligned set of states, let's say, and in another world, you're just discovering that they were already in a disaligned set. So you're uncovering facts about the world that are already inhere. And on the QBist perspective, you're saying, no, there are no facts to be uncovered here about the world. We're just updating our beliefs, and therefore there's no kind of instantaneous change in a state of reality that's caused by
So
experiment.
just to rephrase this, so this entangled state you're talking about between is the state of a particle here and a particle in a distant location is always the state of one agent. So for instance, if I'm here and I have a particle here and a particle over there, it's my belief about what I would find if I walked over there and made a measurement on the other particle. And so when I make a measurement here, then I only update my beliefs about what I would find if I walked over to the other particle and made a measurement there. So that's how QBism just gets rid of all that non-locality nonsense.
It is a very nice explanation. I want to come back to another kind of aspect of realism, or rather, I guess, argument for there being something real to quantum states, and it goes something like this, which is that if you have under the Schrodinger equation or other equations of quantum mechanics, quantum states evolve through time, even if you're not interacting with them. And the kind of QBist perspective on this seems to entail us to believe something like, or the following, that we need to be kind of continuously updating our kind of epistemic beliefs, even though we've not received any new information about the world. The only information that we've received is that sort of time has passed. I'm not saying this is a knockdown argument, but I feel that's kind of unintuitive. And in that, generally, I can't think of any other examples where we want to update our beliefs unless either we have received new information about things, or we feel that there is some time-driven physical process which would be causing things to change independently of what we're doing. Is this, do you feel the same difficulty here? Is this something that QBists need to grapple with, or is there a kind of straightforward way of avoiding this?
It is something that QBists have to address, and we have very clear ideas about this, but they are I don't have a very good non-technical way of expressing that. But here's an example of a situation where you actually do change your beliefs without any actual, new information. So it has to do with a famous, insight of the philosopher von Frasen, his reflection principle. It's about you are thinking about how you should gamble, let's say, or how you should act at some future.
Right.
As some future said. So basically, you are trying to let's say you're forced now to put down bets on some events at a future moment, and so there are some principles and ideas of how you can actually formalize that in a coherent way, which bypass or actually destroy your dichotomy of updating because something really happens in the world, or because you actually had an interaction with the world. So you can actually there's interesting ideas in that direction. But I definitely agree. It is something that needs attention and needs further work.
Yeah, I feel it. I think Harvey Brown at some point commented that sort of what's mysterious for most interpretations of quantum mechanics is the apparent collapse, and that's what they try to that's what they grapple with. And on the qubit side, it seems to be a little bit the reverse, and it's the kind of evolution of things independently of agents' interactions.
Yeah.
Could
So
I don't know if you could.
it's evolution. Cubists would never say the evolution is happening out there in the world, because the evolution will always be the the change of an agent's beliefs, because the evolution affects state vectors, and state vectors are not existing out there in the world. So therefore,
Right.
the evolution happens. It's about the evolution of the expectations of the agent,
And could you
and
maybe? I'm not familiar with. Sorry, I was going to
it,
say. Go ahead.
well, all I was going to add is that the way that happens, and the way Hubris would actually describe this, and answer the question of why should the expectations change in this particular way, is something we're working on.
Okay, good. Okay, I'm keen. I don't know if you can sort of restate the reflection principle of Van Fersen, because I thought that was really interesting as a potential, just to have an example of where one might be kind of justified in updating beliefs without there being some sort of new information coming through. I'm not familiar with the principle, but did I understand it to be something like one is reflecting, one just thinks hard about things and therefore ends up changing one's strategy? Is that how it works with betting, or is it, have I completely got it
So
wrong?
what you do is you consider receiving more additional information. Sorry, you are considering now receiving additional information, or doing an experiment in the future, and
Right.
um, and so and that means, since you are planning to do this experiment in the future, you already now change your your betting, let's say, strategies for these for for events that happen even further in the future. So you consider
Okay.
this intermediate experiment, let's say, and simply by considering this, or by planning, considering this intermediate experiment in some way, maybe gathering more information, you will already change your your commitments now. So
Okay, I think
reflection
that
in
makes
that
sense.
sense
Yeah.
means, I think, reflecting back from the future time to your present expectations and beliefs.
Right.
It
So
wasn't
yeah,
a very good explanation, but
no, I think that
I
makes
think
sense.
that's
I mean,
roughly the.
it's certainly more cashed out than just one thinks hard, right? It's one thinking
So
it's
they're
carefully
good.
in a
They're
specific
very
way.
very good examples of that in, let's say, things like option pricing or so, where you ask yourself, well, how much should I pay now for an option that that and the for some stock option, and it depends on your expectations of the various things that might happen, that might happen in the future. So that is pretty exactly an example of Van Fraasen's reflection, option pricing.
Okay, that's interesting. I I'm sort of wondering whether I have sort of more arguments of a similar vein as to, and I'd refer listeners to Harvey Brown's got a talk on where he talks about sort of plausibility arguments for the realism of the wave function. I think he's actually quite. I think he goes on the record as saying none of these are like knockdown arguments either. They're just reasons why there's some explanatory weight to, or appears to be some, useful work that the wave function is doing for us. I might just kind of trot them out in case you want to sort of fire them down. Although I think we're probably not going to do either the objections or the responses complete justice in the time we have. But there's things of the type, well, interference we can understand via the wave function, and it gives us quite a nice explanation for things like the two slit experiment and just thinking in terms of kind of objects that feel familiar, waves. Another nice one I think is, and maybe I'll finish with this, is around the exclusion principle, and that so for fermions, so for half integer spins particles, you have obviously they can't occupy two identical particles can't occupy the same quantum state. And there's a kind of explanation via the wave function which goes, well, fermions are defined by if you swap them between two different states, there's the wave function changes sign, and therefore you can't have two in the same state, because you'd have one in the same kind of real state of affairs having both a positive and negative sign, because you could kind of swap those two. And that would kind of point to, well, I mean, I think there's probably other ways that one can draft the exclusion principle or possibly explain it. But yeah, curious to get sort of like the brief QBist response to objections of this type.
Well, I have a very simple and response, which is the explanation you just gave, were in terms of wave functions. Now, if a QBist agent, if the QBist agent writes down these wave functions, then exactly the same explanation will be available to him. The wave function expresses the QBist belief about the system, and then as a consequence of that, you find the exclusion, because the exclusion principle is basically a property of the wave function you write down.
Okay, so I guess
explanation does work slightly different in QBism. Yes, a QBist would say the following: people always demand an explanation. QBism says especially we don't explain. It's just a guide to action. But you could actually argue the following. So imagine I have a web of beliefs, which obviously is not just writing something down and pulling it out of a hat, but it comes from very hard work and taking. I mean, you have to learn physics. You have to really work very hard to get a consistent mesh of beliefs, because what the normative rule is very demanding. It tells you have to be consistent, and there's lots of information, lots of measurement results, lots of theoretical considerations, and you have to work very hard to make them all into a consistent measure of belief. From all this come the wave functions you assign to particular systems. And now you predict something to happen with probability close to 1. And then the typical sort of challenge to QBism says, so here you have something. How do you explain this? Mm-hmm. And the QBist will answer, what do you mean? Why should I be surprised? I predict this is happening with almost certainty. So what more explanation do I need? I would be surprised if it didn't happen. Then I would have to think back and look at my assumptions, etc. But if all this big normative enterprise of coming up with a consistent picture leads me to a probability close to 1, and then the thing happens, there's nothing further to explain.
Yeah, I think that's like what this comes down to is maybe what is it that we expect our explanations to do? And if we're expecting them to sort of remove surprise, then clearly that QBism works, right? Because you wouldn't be surprised in that sense. But I think that sometimes we're demanding something more of them, which is not just sort of telling us what we should expect to see, but actually sort of grounding that in something, in some elements that are out there. So I think you can kind of, maybe depending on your theory of explanation, it might affect whether you kind of the attraction for QBism versus other interpretations. Does that sound right?
Well, yes, but I also would say that Cubism very much wants to ground things into something bigger, into a picture of the world, and it's just in a sense is more ambitious. We don't want to ground it simply in a mechanism that uh, explains or describes everything that physics has to deal with. Physics deals with, which actually, I mean, I believe is only a small part of the world. So that's maybe the biggest difference. For qubist physics, quantum mechanics physics is a small theory. It has a specific role. It's extremely successful in what it's doing, but it's not everything there is there. It's not the whole world. And so Cubism's big project, the philosophical project, is to say, well, we physics tells us a lot, and and what does it tell us about this bigger world, the world beyond physics? And the premise there is that physics is a small theory, which is, of course, diametrically opposite to lots of other approaches which hope to, to find to which hope that physics in some sense captures the whole and everything else is emergent.
Yeah. Yes.
So
yeah, I think there's something very humanistically attractive about Cubism in that sense. That and I kind of goes back to your comments earlier that the universe is unfinished, right? Whereas in like a multiverse approach or many other ideas, you can kind of think of it as this great static thing in time, which in some emergent manner is producing. Well, sorry, it's not even in time; it's just outside of time, right? But in some emergent manner is producing within us the perception that things are going on. But in another sense, it's already determined and written. I do find that is a kind of attractive viewpoint. Certainly, I somewhat worry that its seduction is kind of leading on away from the real parsimonious theory, which would be and it's unusual to call many worlds theory parsimonious because it posits a lot of worlds, but in other ways it is parsimonious in terms of not sort of stepping outside of that physics viewpoint of things and just saying, well, all we have is kind of the normal sort of stuff that we've been thinking about for thousands of years, and we don't need to introduce this new element of where the world and the agent touch. I'm curious, do you have aside from maybe the kind of palatability of some of the consequences of many worlds, do you have kind of other objections to it, or what does it all sort of derive from?
okay, well, let's just. I know that some people find comfort in the idea of the world being deterministic, and really, quantum mechanics to be all there is. Now, there I can't really say much against. One key objection for me is, I mean, there are problems in details in, for instance, what's the number of branches, what exactly triggers branching, all kinds of things which I do not think have been worked out. There's a big problem for me, and I've once contributed to a paper about that, actually understanding and interpreting probability in many worlds. I know that many worlds proponents believe the problem has been solved. I disagree with that, but we cannot really, I think, get into that now. Problem is if everything behaves deterministically and everything happens at once, what's the point of probability is what to do. And of course I know the attempted answers, but there are also rebuttals to these attempted answers. then there is, I believe, what's a total lack of. So it's probably asking too much of many worlds, but it's probably, I don't think it's unreasonable. So you start with this conception of having a wave function of the universe and a time evolution of that. Well, that's just really, if you, it's probably too technical a term, but this is a Hilbert space. It's just a vast dimensional Hilbert space and a single vector in there that sort of rotates a particular way. Now, it seems to me that there's no way, just if you're given that, there's no way of getting to down to the actual world we see in all its richness. So I believe that many worlds has to cheat and has to take the world as it's given to us and all its marvelous richness and beauty and so on as a starting point and given, even though it claims that the starting point and what's really there is this abstract thing out there. So I think that's cheating. But that's just my. None of these are, of course, knockout arguments or anything. There is one way. I mean, we're not going to decide this now, but here is one very good reason for taking QBism seriously. It exists. It's a possibility. It's empirically adequate. So, but just by doing physics, you're not going to be able to, because interpretations of quantum mechanics, as long as they are coherent and consistent, make the same predictions. So therefore, there's no way of doing experiments to distinguish between them. Now, just the very fact that there exists an interpretation of quantum mechanics, QBism, which according to which the world is unfinished and much richer than what physics alone can tell you about, is, I think, exciting. And as you know, as I said, I believe that there are very strong reasons in the quantum formalism to go towards QBism. So actually, it's more than that. For me, it's there's the arguments for QBism are much stronger than just saying, well, it is a possibility which is entirely consistent with everything we know. But even if you had only that, if you only knew QBism is a possible interpretation of quantum mechanics, then that means you should actually really look into it, because it paints a world which is very different and actually very exciting, very different from the one that's painted by the same many worlds.
Yeah, I think that's I'm going to say that there's for me, a very loose analogy here with kind of Pascal's wager, in that you may not have sort of, I mean, as you said, there's arguments coming from the quantum formalism itself that motivate QBists to take this perspective. But there's also a separate tug, which is the one for me somewhat analogous to Pascal's wager, which is that it just gives us a nicer view of the world in terms of, or one that's maybe more comforting. I don't want to be provocative in the use of that word. I mean, or liberating perhaps is a better word to use. Certainly one which makes agency not just an emergent, rather tricky thing to explain, but a kind of fact within the world. Even though agents, as you say, can be themselves subjected to analysis by other agents, there's something special about agency, and it's what makes the world unfinished. I buy that. I like the feeling of that view, even though I feel like, as I said, I'm being seduced away from something which is maybe sort of more realistic. Another point, actually, I just want to get in another point here. I heard Dean Rickles comment, and I don't know how strongly he subscribes to this, or if it was a throwaway sort of comment, that one can kind of view the different interpretations of quantum mechanics as, if you like, having the status of different coordinate systems within relativity, or let's say kind of different gauges. So, as you say, there's no necessarily empirical difference between most of them. Some of them do make different empirical claims, but most agree on the predictions that you'll get out of quantum mechanics at every level. So there's kind of a question, well, what are we arguing over, right? Of course, I think we both feel that we are arguing over something substantive. And maybe that's the biggest kind of agreement between all the different people trying to interpret this, that it's not just enough to get the predictions. One is the QBist, the Everettian, even the hidden variables folks are trying to look for those kind of elements of reality, and we're just disagreeing on what they are, those kind of explanatory factors. Yeah, so I don't know how much sympathy you have for this kind of view of things as just, or interpretations just as coordinate changes of reference. But I feel like we agree these are important questions.
Yes. No, actually, I don't agree, because if you sorry, I don't agree with Dan Rickles' point of these just all being just coordinate transformations and just looking at the same thing from a different angle, because I think one of the big differences between QBism and mostly all the others interpretations, or the majority of them, is that QBism does not think of quantum mechanics as being a description of the world in any way, and also not exhausting the world. It's a small theory, whereas all the others are big theories. They actually try to capture the whole, whereas QBism, quantum mechanics only captures a small thing. So therefore, I don't think that this coordinate transformation view is correct here. But so, yeah,
I mean, I think that's another
of course,
point.
the reason why we
Certainly
argue
agree.
is because we want to learn what the world is like, and so we are trying to explore as much as possible, well, what worldviews are compatible with quantum mechanics, because we all believe that quantum mechanics is correct in or is an almost successful theory, and so we want to know how what does it tell us about the world, and we come to different answers there, but
yeah. I think we start at the same point in that quantum mechanics is itself sort of not wearing its interpretation or its meaning on its sleeve. I sometimes think of William Harvey's theory of blood circulation as just like a great example of a theory where the predictions and the claims on reality are sort of so transparent that there's kind of no divergence between the two. Whereas quantum mechanics is this thing where everyone's agreeing on the predictions, but the claims about reality, everyone seems to be disagreeing, sometimes very acrimoniously as well. But yeah, I think again, it's important to take seriously this business of trying to figure out actually, what is behind that predictive success. I mean, you sort of ahead of being, or prior to taking this role within QBism and developing that program, are a professor of mathematics and have worked many years on quantum information and quantum cryptography. Has QBism changed your practices as a scientist in that role, or given them a different flavor?
that's a very good question, and actually this is one thing where I think we might be able to distinguish between interpretations in a different way. So an interpretation is leading you towards the kind of questions you might ask. So the mathematical theorems or the mathematical questions concerning quantum mechanics that you work on or that you find interesting depend on your interpretation. And so you can ask what interpretation is most fruitful in terms of the questions it suggests, and questions which are important. And so one of the theorems that came out of QBism that I proved together with Chris Fuchs and Carl Caves, the quantum definity theorem, is a very good example of that. So the quantum definitive theorem tries to answer the question, what do we mean when we talk about an unknown quantum state? So if you think of the quantum state as something out there in the world, then it's obvious what you mean. Well, there is a system, it's got what the quantum state is just unknown, we want to find it out. In QBism, that's not available to you, because the quantum state is always an agent's bundle of expectations, if you like, and personal to that agent. So what do you mean by it? And so the quantum definitive theorem answers that question in a operational way and shows exactly what assumptions you make in order to so that the mathematics that people use to find an unknown quantum state applies. So it identifies exactly what assumptions are behind the very idea of an unknown quantum state, and so that's a it's a direct answer to your question. This is something where my interest in interpretation has directly affected the kind of work I did, and there are other examples of that. It
I
also
think
actually is the quantum definitive theorem also goes further. See, science relies very strongly on this notion of repeatable experiment. Now, any experimenter will tell you that the repeatable experiment is not an obvious primitive, because you have to work extremely hard to make sure the conditions are the same, and it's actually not even totally defined what that exactly means, because there's a lot of circularity in there. So there's no way that the idea of repeatability is just obvious and you just look at it and define it. And so the assumptions in the quantum definitive theorem are actually, in some sense, you can say them, they're very precise mathematical assumptions that characterize what you mean by a repeatable or by a repeated experiment. So a bold claim would be that QBism, and it's a bold claim, is in that sense more fruitful than other interpretations because it leads to more interesting mathematical questions. But I'm sure you could rebut that in some way. So.
I mean, I think the weaker claim, and I doubt many would disagree with this, is that there's value in having a multiplicity of interpretation. So, in the spirit of Dean Rickles' comment, while I think it's important to acknowledge that there are significant differences between these interpretations, that doesn't mean they should be, we should put all our efforts into one of them. And I feel there's probably, there's different research programs being encouraged by the different interpretations. I think the many worlds folks would point to quantum computing itself as something that's quite naturally suggested, and I think David Deutsch did this from that interpretation, and it gives you a nice handle on what seems to be going on in quantum computers. And I'm sure you can kind of rephrase that and say, well, the QBist perspective, we can account for that too. But it's more that, they suggest different ways of thinking about things and probably provoke one. Yeah.
I'm a great fan of a paper by, I think, Andrew Steen with the title "A Quantum Computer Needs Only One World." But, but it's an interesting debate on whether many worlds really gives you a better handle on quantum computing. I don't believe so, but I don't think we can get into that here.
I think that, I think that's right. And I'd say the many worlders would say, well, we might have gone along to looking at, some of the problems in mathematics that have been inspired by the QBist approach. Actually, Andrew Steen was one of my lecturers when I was at Oxford, so I sort of remember him, although we never got to that level of discussion in his lectures. But I wanted to ask one other so I've asked the question how it's affected you sort of professionally. Bigger question, how has QBism changed your view of yourself and of humans in general?
Well, that is
I'm sort of asking you to summarize everything that you said in a sense.
I am. I'm more certain in my belief that I, as a human being, are autonomous and free, and that I'm a free agent, and that I have free will, or that I am an autonomous agent in the world, and I'm not affected by all the arguments that people constantly cite and sort of in the press and in articles and in discussions that physics actually tells us no, it's all an illusion. It's in popular culture. It's a very powerful idea. Physics, everything, the whole world evolves according to physical law. Therefore, well, free will, human agency is just an illusion, and it's a powerful idea. It's very often quoted, and it's if you have a traditional view of physics, it's seductive, it's worrying, and I have left this completely behind. I just believe in human agency and the fundamental role for us in the world.
Yeah,
in an unfinished world that I can potentially change in probably only minor ways, but
I think it's a lovely sentiment, and I mean I agree. I think we do have agency, we do have free will, but the route I get there is very different, and it's sort of the same sort of route as one would use for explaining, I don't know, why it makes sense to believe in, I don't know, sheep or something, given that sheep are just loads of, what physics doesn't say anything about sheep. Like, why should we believe in them? But I will warrant that it seems that the QBist picture, again, provokes that or encourages that thought in a much more direct way than other interpretations. Yeah, I can't think. I mean, I think this is a good and positive note to finish on. That we're finishing this podcast, but it could end in many different ways. Like in these the universe is not written. We're co-creating it right now. We're participating in realism, but not in a sort of us being in a box sort of way. We're pushing on the walls of it. Yeah, it's been a real pleasure speaking with you, Ruediger. And I know there was some kind of trepidation about meeting someone from the other side of the the chasm, as it were, the abyss between interpretations. But I feel like we have a lot in common, right? We agree that this is an important thing to think about. We go very different routes from there, but I found this a really interesting discussion.
I thought so too. Thanks a lot for asking good questions, and it was a very good experience. Thank you.
Thank you.